yeah, we got a level 2 question now. All right, now what makes this a little bit harder is that it's not just simple kind of plug and chug and rearrange the equation type thing. That was like algebra 1 stuff. This one's got a little bit more skill involved in it, a little bit more thinking, depth of thinking, kind of critical thinking here. So in this question, a student's been asked to determine the acceleration of a ball that's falling through the water. Okay, so you might have well, I guess we don't know what we have. You get to come up with that. So the acceleration of a ball falling through water somewhere. The student makes the assumption that the ball falls with constant acceleration. Now, AP will do this sometimes. They will ask you to make this assumption. Whether that's a good assumption or not is not important. You have been told to make this assumption, constant acceleration. So we're going to make that assumption that it is constant acceleration, and we'll worry about the rest of it later. Okay? There may be a question later where it actually says, is this a good assumption, why or why not? But for now, if it says to make that assumption, we're just going to go with it. All right? Using materials found in a normal high school classroom, design an experiment that would allow the student to determine the acceleration. All right? So, drop a ball into the water. Somehow we need to figure out acceleration. Okay? Clearly indicate what materials are needed. All right, now I hope you're already kind of thinking about this. You need water and the ball, and you need something to hold the water, right? Now, the more distance that you have, the more precise, the more accurate you're going to be able to be, because there's going to be less error, right? If you have a really short distance, it's really hard to start and stop your stopwatch, even with like a slow-mo camera or something. In fact, that's probably actually a really good idea. I just thought of that one. So we need as much distance as possible. So perhaps we use, and you guys probably use these in chemistry, we use some kind of graduated cylinder, right? And the graduated cylinder, we can fill that up with water, and then we'll take the ball. And so we need a graduated cylinder, we need water, we need the ball, and we need whatever, I guess in the next part, it's asking us what are we going to measure and how are we going to measure it. All right. Now, let's think about, in order to calculate acceleration, what is some of the information that we can gather? What is some of the information that we can use? What can we measure? All right. Now, hopefully you're thinking about the kinematics equations here, because you don't have a lot more physics at this point. So this is kind of what we're stuck with right now. So think about, what of those variables could I possibly measure when I hold this ball and drop it into this large container of water? Okay, well, hopefully you're thinking, well, position is pretty easy to measure, right? I could add in like a meter stick here and either put 0 up at the top or put 0 at the bottom. I think it'd probably be easier to put the 0 of your meter stick down at the bottom, and maybe it goes a little bit higher like this, right? But we could use the meter stick here to measure your position. So this would be a good situation, good example of a situation where we're not going to start at 0. I'm going to start at whatever the height of the cylinder is, right? I'm going to start right there. In fact, one of the things we'll talk about here in the description in just a minute, but where we put the ball is going to be important. So we're going to use a meter stick. That'll help us get distance, right? So that'll give me both the initial position and the final position, okay? Initial velocity is pretty easy to measure, right? If I hold it at rest and release it, the initial velocity would be 0. So I think we can go ahead and go with that one. So in order to calculate acceleration, I now need either the time or the final velocity, right? I can either use time, and then I could use this equation right here because I already got position and velocity, initial velocity. So either I can measure time, or I can use this one down here because I've got position and initial velocity. But in that one, I'd have to measure the final velocity. So what do you think is easier to measure? Is it easier to measure time, or is it easier to measure velocity? Well, I tell you, for something falling through the water, it's probably going to be a lot easier to measure time, because we can't use a motion sensor. There's no way to directly measure the speed of that ball. We can get average speeds, but the actual speed at that point in time would be very, very difficult without some type of other maybe computer system or app or something like that. So probably time. And so how would we measure time? Probably using a stopwatch. Now, my recommendation to you, anytime you use a stopwatch, is to also use a slow-mo camera. Okay, and it doesn't have to be a fancy one. The school gives you an iPad, you can use your iPad, right? Your iPad has a slow-mo setting, you can record it. So what you do is you put both the ball, the ruler, and the stopwatch all in your frame, and then you hit record, start the stopwatch, and the stopwatch is running, that's fine, and then you can do the whole thing with the ball, and you can figure out how much time it takes to get to each position. All right, so what will we need to measure and how will we measure it? We're going to need a stopwatch, a ruler, and a slow-mo camera. This is going to be used, the stopwatch is going to be used to measure time, the ruler is going to be used to measure distance. All right, the slow-mo camera is not being used to measure time or distance, but it's going to be used to help us capture that to decrease our amount of error. Okay, so it's important, don't ever say, I'm going to use a camera to measure speed. You can't use a camera to measure speed. Camera just takes a picture, takes a whole bunch of pictures and puts them together so it looks like the pictures are moving. Okay, camera doesn't measure that type of thing. You might, if you have a timer on your slow-mo, you might be able to measure time. But it's usually better to just put the stopwatch in there if it doesn't have anything like. There are some apps that'll do that for you, but unless you have that, stopwatch is the way to go. All right, so we've talked about what we need. We've talked about what we need to measure. Letter C, give a detailed description of your recommended procedure for the student. Now, here's where it's going to be important that we really, really give some detail. Okay, so we fill up the container to a specific level. Now, you may fill it all the way up to the top, or you may say, I'm going to fill it up to 50 centimeters because that's going to make my measurement easier later. It's totally up to you how you want to do that. But be very clear how much you're going to fill it up. Okay? Now, when we drop the ball, you don't want to drop it from the position that I've measured, that I've shown here. The problem is that the ball isn't in the water now. And so when you release it, when it hits the water, first it's going to break the surface tension, which is going to change your acceleration a little bit. And then once it's in the water, the acceleration is going to be different than when it was out here in the air. So a much better thing to do would be to state in your experimental design that we're going to hold the ball just under the surface of the water, measure its height, then we're going to start the stopwatch and turn on the slow-mo camera and release the ball. And the ball is going to fall. And what else are we going to do? We're going to measure various points along the fall. Okay? You could just do final and initial, but why just one? Do multiple, right? Measure from here to here, right? And that's your initial and final. And then the time, the difference between this time and that time would be your time, right? And then using the same video, you can get from here down to there, right? And so you can get a second, you can maybe say, let's do the first 10 centimeters and then do another 10 centimeters. So now I'm dropping 20 centimeters. So your displacement would be 20, and then your time would be the difference between here and here. And then let's go another 10 centimeters, right? And so now I've got from the top down to there. And you can get all that from a single video, right? You can get multiple data points, okay? Now, of course, you could just put it underneath and drop it and measure the beginning and the end and do that multiple times, okay? No matter what you do, anytime you give a detailed description, you want to make sure that you are giving some way that's going to help you to decrease the uncertainty. All right? Now, how are you going to use the results to determine the acceleration of the ball? Well, you've got a couple of options. Okay? One option is just to take each of those initial and final positions and the difference in time and put that straight into my equation here and solve for acceleration, 5 different times. And hopefully the acceleration is more or less constant. So that would be one way to do it, is just use the equation for each of those positions. Make sure that you're very clear with how you measured that, how you get the time by taking the time of the stopwatch here and subtracting the time of the stopwatch there, so that you get the actual time between the initial and the final. Initial and final, initial and final, right? So make sure that you talk about that. The other option is actually the better option, because they love to see graphs here. Graphs is like their favorite thing ever. If you show a graph and your graph is good and nice, that's like points. You get more points for that. All right. Now, the way that we would do that is we would create a graph of position versus time. So when we create this graph, we could start with our position being 0 here. Whatever that number is, we're just going to make it 0. And then go 10 centimeters from there, right? And so then we'd go 10 centimeters from there, 10 centimeters from there. And then get the times, because we can use the times from our slow-mo camera, whatever the time was that we released it, and then whatever time it was when it got to this point, and then subtract the two. All right, we should be able to get that time. Now from that, we should be able to get kind of a graph, right? Once we get our graph, then you can use that linearization process that I taught you, and you can actually linearize the graph to help you determine what the acceleration is, right? And so essentially we would say, well, we would plot the points on a graph, we would linearize the graph. Now actually you might be able to figure out what you need to do to linearize that graph. If you think about the equations here, if we make our initial velocity 0 and our initial position 0, then essentially we just have the equation x equals 1/2 at squared. So you might be able to notice that if I go this on the y-axis and t squared on the x-axis, then the slope of my line will be 1/2 a. And so then you could say, well, I'm going to plot the points with x versus t squared. Then the slope of my line will be 1/2 a, and I can calculate the acceleration from that. All right, so that is the best way to do it, and I hope that we can kind of push you all in that direction, push you lightly, nicely, kindly in that direction at this point. If we get further into the year, it may be a little more of a shove, but for now, if we can kind of move nicely in that direction where when we are trying to use our results, we are somehow creating and analyzing a graph, that's where we want to be. The reason why that's better is because that will take all of your points and look at them all at once, rather than finding individual values and averaging them. Now, finding individual values and averaging them is better than getting one data point, but it is much better to do a regression and to be able to come up with a single slope that contains all the points, or at least tries to fit all the points, because sometimes if you just average numbers, one might have a larger effect than another, and things kind of get messy in the mathematics. But if you draw a single straight line, because we've graphed x versus t squared, you should be able to draw a line that fits the data the best, and then get it from that. And that is always going to decrease your error significantly more than just finding values and averaging them. All right, so that is example number 2. Recognize that the math wasn't too difficult, the physics wasn't actually too difficult. The main reason for putting this here was to start getting you to think about experimental design and what's the best way to do this, and what are some details that I should think about and mention when I'm writing. One of the things I see students do a lot is just kind of write down 3 things. Drop the ball in the water, time the ball, and measure the height of the ball. That is absolutely nothing. That means nothing to someone who's trying to do the experiment. So details. Hold the ball just under the surface of the water. Measure the height up to where the ball is. Mark off. You could even mark this on the cylinder. It would be easier to see in your slow-mo if you just measure from there and you mark off 10 centimeters on your cylinder, and then mark off 20 centimeters and 30 centimeters and 40 centimeters. And they'll be a lot easier than to be able to see at what times you reach each of those things. You get what I'm saying? The more detail you put there, the better off you'll be when it comes time to actually have to do this on the AP exam. And I guarantee you, you will see an experimental design on the AP exam because that's one of the 5 types of questions that is guaranteed to be on your exam. So, good start here. Hopefully that was interesting to kind of see and talk about. And let's move on to a level 3 question.